YouTube right now and live stream on Discord. Why is the link for set theory using quantifiers a bit different? I'll get to that once I get the screen share up and running. There we go. Alright, so I'm not really quite sure what the question is about. Why is the link for set theory using quantifiers a bit different? I'm not sure whether that person, Armand, is referring to the URL itself, or oh, you mean how it looks like? Yeah, one is embedded. The other one would open as a new tab. That's all. I mean, that's the only difference. See, now it looks about the same. Cool. All right. So, okay, excellent. I think from now on, I might decide to refer to people by their avatar. So I'll be the big orange, the fat orange cat. I think that will encourage people to use to choose their avatar more carefully. I like my avatar too. Naruto is cool. Before long, we're gonna end up with some discussion, of Naruto versus Goku versus Superman versus the strongest person in MCU versus yeah, exactly. I like Garfield. I like my superpower too. I'm not sure whether I talked about my superpower in this class or was it in the assembly language class. The type as a whole, okay, if you do your Myers-Briggs type indicator thing, my type is specializing in killing time. So I think there's really, if you can kill time, I would say that's a pretty big superpower. All right. So what we'll do now that it's 31 and a little bit beyond that, so we'll go ahead and start with the quiz, and I am going to show you the answers, and I will also start to explain the answers, why a particular choice is the answer of a particular question. So if you have any questions, like if you are not really sure, about the reasoning or the exact term, that kind of stuff, it might be a good idea to ask questions along the way. And that's kind of the advantage of a synchronous class is, we are all doing this in real time. You can ask questions, I can answer questions. Why am I showing the answers? Because I want to talk about it. It's due today, right? Or is it not? Yeah, it's due today. Or not? Did I? Okay, let me double check. Attempt due, it is today at 4:30, so I'm going to talk about it. I think so. I think you guys can see your own answers. I can check that later. Alright, so I'm just going to go over this. Question number 1, A has the elements of A and B. B as a set has the elements of A, B, and C. Which of the following is true? And in this case, only one can be true. Alright, so the first one is A is a subset of B. That is true. Okay, so I would intend to click this one, but I'm going to check the other ones too. Okay, I will adjust the your own answer thing in just a little bit. So let me do this first, okay? And then I'll open it up so that you guys can review your own answer. Or I can do it so that you can see your own answers first. Okay, let me take a look. And this is about, oops, okay, I almost Almost spilled my coffee. That would not be good. Alright, so we go to edit and we'll click let students see their quiz responses and see the correct answer. So everything should be good now. Click save. Alright, so if you refresh your browser and then click on the assignment or the quiz, you should be able to see your answers along with the correct answer now. Alright, so back to question number 1. But I really want to make sure the other ones are not correct answers. So we look at the second one. A is an element of B. No, A is not an element of B. Uppercase A, which is a set, is not an element of uppercase B because there's no element in B that is a set, period. B is a subset of A. That is not true because B contains an element that A does not have. B is an element of A. B is a subset of A is wrong. Okay, that's the previous thing. I'm not sure whether I said the right thing or not. But B is an element of A is also false because of all the elements of A, none of them is a set, let alone a set that has A, B, and C as elements in it. All right, cool. Alright, so if A and B were made of sets, could we use elements of and subset interchangeably? The answer is no. Those two concepts are very different. One is asking whether a thing is a component of the second. The other one is asking, okay, both are containers. The other one is asking, is everything in this container also in the other container? So they are definitely not interchangeable. So what about if A equals to the set of A and also the set of B? What about that? You mean to answer these questions based on the change that you have suggested? Okay, so it would be false for all of these in that case. So A is a subset of B is not true. A is an element of B is not true. B is a subset of A is not true. B is an element of A is also not true. Okay. All right, so with the second change, then it would be the same answer as what we have now, which is A is a subset of B. Element of is about containment. Subset of is about everything that I have, you have too. So those are very important core concepts to differentiate between is a subset of versus an element of. So let's move on to question number 2. So question number 2 has checkboxes instead of radio buttons, which means at least one can be checked. Okay, so we'll take a look at this. Given that the union of A and B has the elements of A, B, C, D, E, and the difference between A and B has the elements of C and E, which of the following combinations of definitions of A and B will satisfy this constraint? So the constraint is this particular part of the question. Select every combination that meets the constraint. Okay, so we'll work on it one by one. The first one has A being ABD and B being CE. So the union constraint is definitely satisfied because if you combine A and B, we'll have all 5, A, B, C, D, E. The second constraint means C and E can only be found in A but not in B. And in this case, it's actually the other way around. So it would not be a correct answer. So do not check the first one. The second one has A, B, C, D, E as elements of the set A, and it has ABD as the element of B. So it would also meet the requirement of the union having the elements of A, B, C, D, E, but it will also satisfy the requirement that elements in A but not in B would be C and E, because you can see C and E are in A but not in B. So this is a possible answer. Option number 3. A only has C and E as elements, and then B has A, B, D as elements. So when you look at the union, which is basically saying, okay, we are looking at a set where the elements can be in A or in B, yeah, that requirement is satisfied because A can be found in B, B can be found in B, C can be found in A, D can be found in B, E can be found in A. So the union constraint is satisfied. The difference constraint is also satisfied because in this case C and E are the only elements in A, but they are not in B. So this is also an answer. All right. So I'm just checking out the text channel and make sure that I am not missing anything. All right, so it looks like it's too good. Okay, third one is not an answer because all 5 elements are only found in A but not in B. So in this case, the difference between A and B would be A, B, C, D, E, and not just C and E. So this is not a good answer. And this is also not a good answer because in this case, the difference would be an empty set because everything in A can also be found in B. So if you want a set that only has the elements that are found in A but not in B, it would have been the empty set. So it's not going to satisfy the requirement of the difference. The next one is also not going to meet the requirement because the difference is going to be an empty set because A is empty to begin with. So if you think about it, if we want a set of elements that can only be found in A but not in B, and A has nothing, that has to be, the difference has to be empty. All right, so next one has ACE in A and then ABD in B. So this one indeed is a correct answer because the union part is easy, right? Because the union part simply says, okay, we have to be able to find, all of these elements in A or in B or both. Okay, it's okay to be in both. It's not a problem. But when we look at the difference, they can only be in A but not in B. And this one does satisfy both requirements. And then the next one has A has CE and then B has ABCDE. This is not a good answer because the difference requirement constraint would not have been met because C and E, even though they are found in A, but they're also found in B. So it does not meet the requirement of not finding C and E in B. All right, so Vector said the order is not important for the difference operator. What do you mean by the order? Like between A and B? The order is important in the case of difference because it is supposed to be found in A but not in B. So one has a negation to it, and that's why they are not symmetric, and as a result, it is important. The other clue why the ordering is important is the borrowing of the subtraction symbol, because in arithmetic, subtraction is not commutable, which means those two operands cannot be exchanged. They cannot change position and maintain the same value. So there we go. Yep, not commutative. That's right, our mind is absolutely correct. All right, very good. Moving on to the next one. This one is very short, but it can also be very confusing. Choose the correct answer. A is an element of a set that has as its own element, as an element, a set of A itself. The answer is false. That is not true. Okay, very good. Number 4. So number 4 is saying, is it true or is it false that a set that has the elements of ABC, is it a subset of itself? The answer is true. Every set is a subset of itself. All right, so next question is, would you say it's correct to view operators as constructing a new set from the two sets it operates on? Yep, that's one way to look at it. It's just like, subtraction and addition using numbers, right? Because let's say we are talking about specifically 4 plus 5, okay? We are not doing anything to the 4, we're not doing anything to the 5. We're coming up with an answer of 9 that is new, okay? So it's the same thing here. So the result of an operator, not a subset, but in the case of union and intersection and also difference, will result in a set. All right, moving on to question number 5. Choose the correct answer. ABC union AB is ABC. That is correct, because we do not want duplicate elements. In other words, we don't want it to be AA, BB, C as the union, because we do not want duplicate elements. Question number 6. These are the fun questions. What is the value of the following expression? So I'm looking at this as an expression, okay? It can be true, it can be false, but I'm not telling you what is A and what is B. So the 3 choices are true regardless of how you define A and B, false regardless of how you define A and B, and the third one is, well, sometimes it's true, sometimes it's false. It depends on how you want to define A and B. So it requires a little bit of thinking, a little bit of understanding of the operators, and just a little bit of time. I mean, this is going to take some time to think about in order to answer. NGL seems obvious in hindsight. What is NGL? Not gonna lie. I see. All right. That is true. Hindsight is always 20/20. Anyway, so let's look at this one and find out, whether it is the first one, the second one, or the third one. All right. So the first part here, which it says, A minus B is an empty set. All it is saying is there's nothing in A that we cannot find in B. Let me rethink whether that's right or not. Okay. So the difference is everything in A that is not in B. So if everything in A that is not in B is an empty set, it means everything in A is also in B. So if everything in A is also in B, that really is just the other way of saying A is a subset of B. Okay, so there are some text going on here. The way I try to do this is by trying to find a statement that breaks the implication. Yep. Or go by the definition and see if you can establish any type of what am I looking for? Counterexample. Based on the definition. And then the next one says, but you also need to look for ones that satisfy the implication. Yep, so you basically just have to look at possibilities, right? You just have to think about it. Truth table, yeah, you have to use different sets. You cannot just use a truth table. You have to basically look at different scenarios. What if A is a subset of B? What if B is a subset of A? What if A and B are not subsets of each other and neither is empty? And so on. So that's one way to approach it. But I'm going to look at this and go, well, the first part really is just saying A is a subset of B. That's all it's saying. And how do I know it? Because I defined subset of using exactly that, right? So if you go back to the notes, you will find that A is a subset of B is defined as A minus B equals to the empty set. Everything in A is also found in B. So the question is, does that imply A is not a proper subset of B? Well, the answer is, well, the implication doesn't hold, okay? So we know the first cannot be the answer. It cannot be true regardless of how A and B are defined. But now we have to differentiate between the second one and the third one. In other words, can we find in some cases that this is false and in some other cases it turns out to be true? Can we find examples of A and B where it is sometimes true and it is sometimes false. So if your head is hurting, that's a good sign, because that means you're at least exercising, at least you're giving it a try. So there are two kinds of people, who would do this and not have their brain hurt. The first one would be, I'm just going to randomly pick an answer. This one, okay, let's move on to the next one. Those people are not going to hurt their brain, because it's just like, they're basically not using it. So if you're hurting your brain, at least you're giving it a genuine attempt. And that is important, because if people are not giving it an actual attempt, and when I explain the answer, it's not going to sink in, right? Their mind is not primed. Okay, it's just like Teflon. You can try to paint Teflon, it's not going to stick. Okay, so by doing it, by working on this, spending time, think about it, you are basically spraying, primer. Okay, and I'm now painting on top of the primer. It's going to stick, so that's a good idea. Okay, so now, okay, let me see if I can. So I am using free plane. Oh, I am not sure whether this is a good time to sidetrack. So probably not a good time to sidetrack. So I am going to open up a new question here and think about possibilities. Okay, so you can actually type equations in free plane. You have to put a backslash LaTeX first. Then you can use the equation stuff that I have used in my notes. Okay, so in this case we have a minus b is an empty set, and that in return implies it is not the case that a is a let's see, subset of b. Okay, so let me see if this works out or not. Oh, look at that. It does work out. Okay, cool. I see you guys are having fun with the math symbols. Very good. I guess I can turn on MathBot, on this server, so that way you guys can also use the LaTeX notation to do it. But it's not turned on right now. All right. So the next thing we want to do is to say, but we recognize the first expression. If you cannot read this, I can zoom in just a little bit. I can zoom in to 150. There we go. All right. So this is our first thing. Okay, so let me insert a new node. Okay, because these are all part of this example. There we go. All right. So next slide. So the next thing we recognize is the first part is simply saying A is a subset of B. Okay, so we're gonna write that here. So LaTeX, LaTeX dollar A is a subset of B. Oh, this is subset EQ because it's subset, not proper subset of. And then we will maintain the right arrow, and the negation of A is just subset, which is proper subset of B. All right. All right. So now we have an implication. So now that we have an implication and both sides look similar, okay, so now we are going to think about cases of how can we make this implication true and how we can make this implication false. All right, so let me catch up on the text channel past the fun stuff that you guys have been doing with the subset of symbol. How did you think of that example? Did you specifically find an example where A is subset of B is false, or just happen to So I'm assuming Ahmad is asking me how or was it somebody else? I'm not sure. Oh, you're asking Jonathan. Okay. I was actually converting Jonathan's logic to proper propositional logic when I crashed. Okay, so I'm not going to use propositional logic. That's kind of fancy. I'm just looking at this and go like, can I find a case where A is a subset of B is false? Because guess what? In an implication, if the left-hand side of the implication is false, the implication itself is going to be true, right? So I just have to find an example of A such that A is not a subset of B. Okay, that's pretty easy to do. So, okay. I just, let me see, undo. There we go. All right, so I am going to make a subnote here, and I'm going to say, let's look at the case where A as a set has X as an element, and B as a set has Y as an element. Okay. So with this particular case, because A is not a subset of B and B is not a subset of A, they really don't intersect, and neither is an empty set. So in this case, A is a subset of B is false already, which makes the implication true. Okay. So I'm gonna just write a little bit more, makes the implication true. Okay, let me get rid of this part here. It's not essential, at least not for the time being. All right. So next, okay, we got another text channel, a text message coming in. I just went through cases where there could be differences given the condition. Okay, we're going to try to find conditions where A is a subset of B, is a more variant other than A is AB and B is ABC. Okay. Okay, so next we want to make the implication false. So how do you make an implication false? If you look at the truth table, and if you're thinking, what truth table of implication are we talking about? Well, that may be a very clear indication that that person may need to review the material. So I'm just going to move forward. So we want to find a situation where the implication is going to be false. There's only one case where the implication, the result of an implication is false, is when the left-hand side is true and the right-hand side is false. So we want to find a case where A really is a subset of B, but A is not a proper subset of B. Okay. Let me see. Maybe we can just make A and B really the same thing. Okay. So we'll go ahead and work out the next example. So LaTeX. So this time we can make A equals to X, and we'll make B exactly the same thing. So B is also just the set with X in it. Makes the implication false. Think about it, okay? Because if A is a set that only has X in it and B is the same thing, then A is a subset of B is going to be, guess what? True. A is a proper subset of B is going to be, oh, okay. A is a proper subset of B is going to be false, but the negation of that is going to be true. No, never mind, this is not going to meet the requirement that I want. Okay, so we want a case where A is still a subset of B, but A is not a proper subset of B. That's what I'm saying is what I'm muttering is what this means. So we want to make this true. A is a subset of B, but we want to make this false, which means A indeed is a subset. Oh, okay, there we go. I just needed to figure out the proper subset part. Okay, so we want A to be an actual proper subset of B, which means B has to contain one more thing in it, like Y, and that would be fine. Okay, so if you think about this particular case, A is a subset of B is true because everything in A is also in B. But if you look at A is a proper subset of B, that is also true. But since we're negating it, it is now becoming false. So now we have the left-hand side of the implication being true, the right hand side of the implication being false, and that is the only case where the implication is false. So we are capable, okay, we ended up being able to make it true for certain configuration of A and B and make it false for certain configuration of A and B. So that means the answer is going to be the third one. It depends on how we define the sets A and B. It is not always true, it is not always false. I'm not sure I have more questions like that. I understand the reason why you asked that question, but right now I don't have any more questions like that. Okay, so let's take row first. Okay, so let's go ahead and take row, and I got it basically prepared, and you guys are gonna like the row taking words. Let's see. Okay, I'm gonna show you the answers. Oh, there we go. You guys can see it. So there are two words. You can choose either one. So the first word you can choose to use, I know you probably want to copy and paste it, is existential. And then the second word you can also use is crisis. Existential crisis. Yep. So choose one of those two words and let me release it. You can't do it yet because I have to release it first. There we go. Save and publish. There we go. All right, so you should be able to do it now, and you have about 7 minutes to do it. Yeah, I chose this particular phrase. You only have to use one word, by the way. So I chose this phrase because, just like killing time, existential crisis is also something that INTP people tend to experience, like a lot. And the reason why I chose existential is because we're going to talk about the quantifiers. Well, once we are done with the assignment. All right. So I'm going to get back to the notes. Nope, at this one. This one. There we go. Who are the chats copying? I think it's the same number of keystrokes, right? Double click, Control C, and then Control V. So it doesn't really matter how long or how short it is, or even matter. Doesn't even matter whether I have a typo or not. It's the same sequence. All right, so Sarah, you might want to join us in the channel that has today's date as the name, because the words are over there. So join the text channel of today's date, not the general channel. So this has been the way that I take roll for this class. All right. Either one. Yep. All right. So I think that's plenty of time for people. That's why I said copy and paste. Don't write. Copy and paste. All right. So we are moving on to question number 7. For question number 6 would be false because both sides are false of the disjunction. Not sure where the disjunction is. This is an implication, it's not a disjunction. That is true. So, but you want to make the expression true sometimes and make it false sometimes. Well, or at least try to. So that's how, if you cannot make that happen, then it will be one of these two. But if you can make sometimes if you can sometimes make the expression true, and sometimes and with other values of a and b can make it false, then it will be the last choice. Yes, the truth table of not x or y and x implies y are exactly the same, because that's how implication is defined. That's what I said earlier, is to use a truth table. Yes. Okay, question number 7. Same deal, okay? This is why you kind of really have to understand what implication is, because if you can say, oh, guess what? The left-hand side of the implication is always false, then you can click the first one, because there's no way you can make the implication false. On the other hand, if you can make, I mean, you guys get the idea, right? You just have to look up the truth table of implication and say, all right, so are we only looking at the first, second, and the last column, or sometimes we can also use the third column? But it is important to understand that the concepts here. So in this case, I'm looking at A intersecting with B, which is a set, equals to A union B, which is also a set. So if these two sets, okay, if the intersection and the union are the same, does that imply A and B are the same? The answer to this one is true. Because when the union and the intersection are the same, that means there's nothing in A that is not in B, and there's also nothing in B that is not in A. Just intuitively, okay? Just intuitively, it means that A and B, there are no elements that exist in only one but not the other one. So in that case, we are also saying that A and B are in fact the same. So in this case, the answer is going to be true. That it is impossible for you to satisfy this condition here, but not to satisfy the other condition. So that's the answer of question number 7. Surprisingly short, or doesn't take much time to talk about it. Question number 8. So question number 8 is sort of the same thing. So we want to look at the implication and say, well, can we find cases to make this true, and can we find cases to make this false? If we can find cases for both, then we are going to use the last option as an answer. If not, then we are going to have to pick one of the first two. So let's go ahead and use mind map. So I'm going to copy the question first, okay? And this is another example. So we're going to go like another example 2. Okay, there we go. And we'll present the question first, which is A dollar A in B, right arrow, negation of A is subset EQB. There we go. All right. So now that we have copied the expression, we want to find out, okay, can we make this true? Oh, that's easy, okay? If you want to make this true, you just have to make sure that A is not an element of B. That is easy, okay? Because now we just have to say, we can make A set that has nothing in it, okay? So A is an empty set, and so is B. All right. So any questions about this example, the way I choose values of A and B in order to make the implication true? Okay. So next, we're going to look at, try to find an example to make the implication false. So how do we make the implication false? Let's find out, a way to do it. In order to make the implication false, the first thing we need to do is to make the left-hand side true. So we have to make A an element of B to be true. A as a set is an element of B. That has to be true. So we will have to make that happen first. All right, so that is not too hard because we can make A an empty set, and then we can make B a set that has an empty set as its only element. Okay, so I'm not saying that this is going to make the second part false, but I'm just going to say, yeah, so we can totally make this, we can make the left hand side of the implication true. Is everybody agreeing that the empty set is an element of a set that has the empty set as an element? I know, this is like, are you kidding me? You just answered your own question tag, right? Okay. But now the question is the right hand side false? Is the negated version of A is a subset of B false? So the first thing is we want to see if the empty set is a subset of B. Guess what? An empty set is a subset of every set. Okay, you can give me any set and I will say, yep, the empty set is a subset of whatever set you tell me. So we definitely make A is a subset of B true. But since we are negating it, so it becomes false. So in the end, this makes the implication false. So that means the answer is going to be, well, it kind of depends, right? I mean, if you choose this as A and B, then the implication is true. But if you choose this particular way of configuring A and B, then the implication itself is going to be false. So because we can find ways to make the expression true and also false, so that means we have to choose the last option as the correct answer in this case. All right, so I'm gonna sip coffee and see if you guys have any questions. It makes A is not in B false. That is what what the second combination is doing. Oh, right. Okay, in the first one, yes, Jonathan is correct. So in the first example, A is not in B. That is correct. So yes. So in this particular case, A is not in B because B is empty. If B is empty, nothing can be in it. Yep, that's right. Okay. Very good. So, so if you are pondering, on this particular quiz, if you're not getting a perfect score, it's okay because all the homework assignments really don't add up to a lot of points. Okay, because the idea of homework assignment is really just to give you something to chew on, to give you something to work on, so that you have an activity that requires you to really understand the concepts, to go back and review the material, to think about it, to come up with examples, okay, to try to think of, okay, how can I make this true? How do I make that false? What tools do I use to do this? Okay, oh, we got the truth table, so we have to use the truth table, find out, how what combination between the left hand side and the right hand side of an operator will return the value of true, and how to make it false. So this is all about that. So let me go back to my mind map, because earlier I was making this mind map and I was basically trying to remind people you might want to have your notes. You should be taking notes along the way, or you should be highlighting something. You should be doing something on your side so that by now you should know what is a conjunction, what is a disjunction, what is negation, what is implication, what is equivalent to, which is also known as if and only if. This is something is in a set. This is the notation that delimits the elements in a set. How do we say the two sets are the same? What qualifies that? Can we have a set as an element of a set? Okay, it covers both of these items. What is this notation? Okay, we are trying to describe properties of elements in a set, because there can be a potentially an infinite number of elements in some of these sets. This is subset of, this is proper subset of. How are they different? How are they the same? How are they similar? This is intersection, this is union. So you really should have understood at least these symbols, what they mean, how they relate to each other, and so on by now. If that is not the case, don't worry too much. Okay, you should worry a little bit. If you're looking at these and go like, I really don't think I'm comfortable with these symbols. Well, it's still in the beginning of the semester. Okay, we're in week 2 right now, so there is still time. Okay, but I would strongly suggest to really spend some time to get familiarized with these operations and symbols and definitions and so on. All right, and yes, all of this is getting recorded too. Just in case someone said, "But Tech, you never told us how to study for this class." Just in case. Just in case. All right. So next, we are going to talk about quantifiers. Okay, so let me see. Where's my quantifier stuff? There we go. All right. So quantifiers are, in English, you have been using quantifiers all along. Okay. And I know how some people like to exaggerate. So I'm just going to use this thing here. And I'm going to start a new node that talks about quantifiers. There we go. And obviously, I am already assuming the entire class has previewed this particular module that talks about quantifiers, because that's what I told people to do last Wednesday at the end of the class. So, what about quantifiers? Well, there are two major quantifiers. They can be easy, they can be hard. Okay, so there are cases where I'm not sure about that one. So the first one I'm going to talk about is, so I will present the symbol first and then I'll talk about it. Okay, so this one is, okay, let's see which one I should talk about first. We'll use for all first, which is also known as the Universal Quantifier. This looks like an A, except it's upside down. Okay. Alright, so this is called the Universal Quantifier. And what does it mean? Well, unfortunately, most people use this on a daily basis when it is not supposed to be used. When people say always, every, all, they are all universal quantifiers. Okay? So when someone said, every class at ARC is difficult, it's so hard, okay, that's a universal quantifier. Okay, when somebody said, every homework from Tech is super confusing, that is a universal quantifier, because what it is saying is it's asserting that a particular thing applies to all of something. Okay, all of something. We'll just kind of call that for now. So that's the universal quantifier. And then we have another quantifier. So the other quantifier is called the existential quantifier, and hence the role-taking word, the choice of role-taking word for today. So this is the existential quantifier. Okay, it looks like an E, except it is left, right, reversed. Okay, it looks like the mirror image of E, uppercase E, except it is, right, left, reversed. So this is called the existential quantifier. Oh, I forgot to mention the typical English words that people use. Okay, so every, always, all. Those are all indicators that someone is using a universal quantifier. Even if you understand the implication truth table, how do you come up with examples to prove it? Do you iterate through the possible combinations? That is a very good question. I really don't know the exact process in my head when I come up with those answers. I just go like, okay, we need to make this true. Okay, how do we make that true? Oh, okay. So I just think of very simple examples to make something true, and then we have to make something false. So I would usually just kind of check, okay, if I make the left-hand side true using this method, what would be the value of the right hand side? Now, if the right hand side turns out to be true, then I'm gonna have to, okay, I need to refine it, which I did in the earlier example. So I'm not really sure how my mind works out in that case. Yeah, iterating is going to go faster and faster as you understand the concepts more and more. It will be easier to work with those operators. All right, so in normal English, what do we use when we want to use existential quantifier? Okay, um, if you're if you're a math professor, they typically will say there exists blah blah blah. Sum is at least one. Those are all clues that we are using an existential quantifier. So Jonathan is correct. Sum is correct. All right. So when people say, well, there's at least one empty parking space in the parking structure. That's an existential quantifier. Okay, it's asserting that at least one of these things exist. Okay, so at first glance, okay, these things are pretty easy to understand. The tricky part is, what if there's nothing? What if a particular statement is applying to something where nothing is applicable? Okay, so that is one thing that we're going to have to think about in just a little bit. But before that, we're going to talk about the symbols. So the way we use the operator is something like this. For all x, p of x. Okay, p in this case is a predicate. So you might be asking, what is a predicate? A predicate is basically a function that takes on any value and it returns a boolean. In other words, you can feed anything. There's no type error whatsoever. You can throw anything at it, okay? And it will give you an answer that is either true or false. So predicate is nothing more than a Boolean function that returns true or false. Okay, so that's what a predicate is. So for all x p of x is basically saying, no matter what you throw at the function p, for everything that you throw at it, it's going to return true. And then existential, if you use there exists x such that p of x is true, that means of all the things that you can throw at p, at least one of those values will make the predicate function return a true. Now, does it mean that, everything else are going to be false or everything else are also true? We don't care, okay? We just have to know that at least one of those values will end up, being true when you evaluate p of x. So p is once again just a Boolean function. So we have Wade typing on the text channel. All right. So I will continue to wait for Wade's text.
I'm writing someone specific. It's not a question.
Oh, okay. All right. So, oh, I didn't know that. I did not know that when you are corresponding to someone else, not to the channel, it would also show your typing in the text channel. Huh. That's interesting. Okay. So now we're combining negation. Okay. So when we look at the negation of there exists x such that p of x is true, it really is exactly the same thing as for all x, p of x is false. If you think about it, it kind of makes sense, right? And then the other one is if you apply negation to for all, if you say it is not the case for all x, p of x is true, it is really saying exactly the same thing as saying there exists an x such that p of x is false. So in a way, it kind of intuitively makes sense. Okay. And then we have section 4 that talks about filtering. Because if you don't do any filtering, the for all really applies to everything in the entire universe. When you say for all, you're basically saying everything that is possible, every value that is possible. So you're talking about all the integers, you're talking about all the rational numbers, you're talking about all the irrational numbers, you're talking about all the complex numbers, you're talking about all the possible vectors, blah 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 blah. Okay, and we seldom would want to quantify something, for every possible value that exists. Okay, that's just not very usable. Okay, that's not very useful. So for the most part, we would like to apply the for all in this particular format, which is basically saying for all E, and we want to filter and say, well, we are not really talking about everything in the entire universe. We are really talking about, it only applies when we are talking about something that is in the set X. Okay, X is just a variable that contains the things that we are interested in. And so when we want to filter, this is how we filter using implication and embed it inside a for all. Okay, so um, let's talk about professors. Okay, I'm pretty sure you guys would like to talk about professors at some point in time. Maybe not now, maybe a little bit later, but at some point you're gonna talk about professors, right? So if P of E is really saying, E is an effective professor. Okay, so P of E means E is an effective professor. Okay, so that means we really should not be applying numbers to this particular predicate. We really should not be applying cars to this particular predicate. We should not be applying administrators to this predicate, because this predicate, it really is specifically useful only for professors, right? So that means we need to do the filtering, and to do the filtering, we would make the set X a set of professors. Now you can say, oh, I only want to talk about effective professors at ARC. Well, in that case, X is going to have, I think, close to 2,000 elements. There are about 2,000 professors at ARC. So then then this particular statement is going to limit to asking, are all professors at ARC effective? That it becomes the semantics of this particular statement. On the other hand, some of you come from, I think so, I have to check. Okay, we have an enrollment of 30,000. So 2,000 professors. Yeah, that sounds too much, but I think it is a lot. At least, I think it's at least 1,000. Maybe not 2,000, but it's at least 1,000. Which is not, if you think about it, it's not too much, because we have an enrollment of close to 30,000. So if you're looking at 1,000 professors to 30,000 students, assuming each student is taking about 12 units, that's about normal, right? Because that's a full load for a student. It's also a full load for a professor to teach. Okay, thank you. Armand found the exact number. So I got the order of magnitude right. Not the exact number, but the order of magnitude. ARC is by far the largest campus of the 4 in Sacramento area. So anyway, getting back to this. So this is a filtering mechanism, which means, if you want to say, I don't really care about ARC, I only want to talk about Sac City, then you change X, the definition of X, so that elements of X will become professors at Sac City College. And once you make that change, the semantics of this statement becomes, the question of, is every professor at Sac City College an effective professor? So this is a very useful mechanism, because we can basically say, we are not talking about everything, we are just talking about these things. And the statement is about just these things. So that is a very important concept, is to be able to do the filtering. So with the existential, we can also do the filtering. I did not quite say, how to do the filtering with existential. It is not using an implication when we are using existential. It's going to be an conjunction. So we have to use a conjunction to join the element of and then the whatever predicate that we want to use to apply to that. So that is how we use existential quantifiers. Yeah, the campus is pretty empty because most classes are online. If something can be taught online, it is online, and I think that includes Chem 400, Chemistry 400, which is a general chemistry, which has a lab component to it, and I believe it is still being taught online. Yes. So that's a very good reminder. If people want to get back on campus, they need to be vaccinated. And I understand some people are concerned about the vaccination. Is actually a procedure to implant a chip into people. If that was the case, I'm going to ask for a refund because I think my chip is not working. Yeah, exactly. $200. The Bill Gates, the Bill Gates chip. Copper based. That's right. Yeah, if it's copper, I'm not sure which part makes it bitter. Because if you taste, now don't do this, okay? Do not do this. But copper sulfate is a bitter, bluish, solution. I'm not sure which part makes it bitter. I don't think it's coming from the copper because otherwise, every cookware using copper would make the food, taste bitter, which is not good. Yeah. The Well, since we are on this topic, it's on my mind. I have to say it. As it turns out, lead oxide tastes a little bit sweet, and I think that's why the Romans, they used lead pots, to cook their food, which also kind of led to, no pun intended, which also led to the fall of the empire, because I think most people got lead poisoning because of that. All right. All right, so Jonathan is asking P of x is true for each e in set x. It depends on what notation we are talking about. Okay. Okay, so I got Wade typing a whole bunch of stuff here. Okay, it's mainly related to whatever the overall argument, which is P. Okay, the predicate is the argument. The implication is just a basic component of a much larger proof. So if you're trying to disprove an argument, you can use implication properties to do so. Okay, so that's predicate calculus. Okay, so I'm glad that Wade is already understanding predicate calculus, but this is a topic that we are going to have to visit in a very different way. Okay, this what Wade has quoted is a classic predicate calculus way of doing things. We're going to do it in a slightly different way for a very important question. And then Jonathan types, for all E is in X implies P of E, and that goes back to what he typed at 530, which is P of X is true for every E in set X. That is true. Okay, that is correct. All right, so maybe I can use a way to illustrate it, by using something that resembles code in a program. So let me open a new tab. All right. So let me just go ahead and write a pseudo function. Okay. So here is it returns a boolean, and this is for each. Okay. And we need two arguments, right? So we need a set x, and then we also need a predicate p. Okay. So the question is, how do we write this particular function. So the way we do this is we use a local variable. Okay, so we have a local variable that I would call result, which is initialized to true. Yeah, so it's initialized to true. And then what we do is we say for, okay, so we have a type called element e, and then we say for e in x, do the following. So I'm not going to make this efficient because all I really care about is the correctness. So I'm just going to say result is result and, this is logical and, p of e, and then after the loop is done, we just return result. Okay, so this is the for each or for all. Okay, so whether you want to say it is for each, for all, every, they all mean about the same thing. Okay, so so as you can see, what if x is an empty set? If x is an empty set, then there's no iteration to go through. In other words, this statement would never execute if x is an empty set because you cannot find any element in x. So in the case that x is empty, result is by default true. Okay? So that is kind of interesting. Okay, it is kind of interesting because what this really means is I can now make some really nonsense statement here and say, you know, every cat with blue blood, oh, okay, blue blood. I'm just trying to make this as absurd as possible. Okay, every cat with blue blood has the size of a grown blue whale. Okay, so I like blue. Okay, you know, this sentence has a lot of blues in it. There we go. So now the question is it true or is it false? Okay. As it turns out, now assuming we are talking about cats that we know, cats on this planet, okay, you know, cat that we are familiar with, there's no cat with blue blood, okay, because cats are mammals and mammals all have red blood. So in the absence of cat, in the absence of this set here, oops, oh, sorry. In the absence, in the case that set x is empty, because result is by default true, so that means this statement is actually considered true. So that is very important. Okay, now it's important not because tag just talks about absurd stuff. Okay, because this actually comes in handy later on when we use quantifiers to define other things. In other words, quantifiers by themselves are, I mean, they're kind of interesting in a way, but only limited. Okay, they are not really that applicable. So we are really just defining the vocabulary that we need in order to define later stuff. Okay, you know, like what is an injective function, what is a bijective function, and so on. We are about maybe a week away from that topic, but we are really just developing the vocabulary to define concepts that are eventually going to be important. Okay, so that's why I throw out these absurd examples, because I want people to understand when you apply this. Okay, because in this particular case, X would be the set of cats with blue blood, but since X is an empty set, the for all is going to return true by default because the result is initialized to true. There's no way to make result false when you cannot get through this statement at least once. So is that concept okay? Is everybody kind of getting the concept of, in the case that the set is empty, the universal quantifier is always going to return true? Okay, because it is important. So now is a good time to talk about the existential, equivalent existential function. So we have bool, and this time we have sum. Okay. And once again, we have a set, confining to what is the predicate applicable to. So we have predicate, which is really just a Boolean function, and this time we have the result initialized to false. So same thing, we have a local variable so that we can evaluate a element in X. Okay, so for each element in X, once again, I'm not concerned about the efficiency of the code. I only want to make sure that it is correct. Okay, so correctness is important, not so much the efficiency. So this time we have result or P of E. Okay, so you can see these two are very interestingly symmetric in a certain way, because we are evaluating everything in the set, and the result is influenced by the application of P of E. Result is influenced by the predicate P of E. The big difference is how we initialize result. One is initialized to true, the other one is initialized to false. And it is also important to understand that one is ANDing P of E to result, which means since result was true to begin with, P of E, when we apply P of E and using it to change result, we can only change result to false. Once result is false, it cannot become true anymore. Okay, so that's why I said this is not very efficient, because once result is false, I'm not exiting the loop. I keep going through this even though there's no chance the result can become true again once it is false. And in this case, it's the other way around. You can see how result is false to begin with, and the only way to turn result true is to find at least one thing in X where P of E is going to return true, because once you have this being true, then the result of the disjunction is going to be true, and then result becomes true. But once result is true, it cannot become false again, because every single time we change it, we're using result's own value in the disjunction. And if at least one side of the disjunction is true, then the disjunction has to be true. So I hope this helps to illustrate in a kind of empirical coding programming way what for all is really meaning and what some or there exist is meaning. Are we okay with these two examples? Okay, great, excellent. And in some programming languages, they actually have this kind of loop structure where you can go through every member in a hash or an object, which comes in handy really sometimes. Alrighty, I'm just looking at the time. We got about 8 more minutes. So now that we have this code, kind of representing what each quantifier is representing, um, then we can continue with the second module, which is set theory using quantifiers. So we are basically revisiting things that we have talked about already. So the first one is equality. How do we, given two items, x and y, how do we know they are the same? So the first thing is, if one is a set and the other one is not a set, then x equals y is going to be false. So you can kind of look at this as the right hand side and the right hand side of comparison having types that are not they're not comparable. We cannot compare these items. So whether they are the same or not is going to be false. So given that x and y are not sets, neither is a set, then we just apply the normal comparison operator. Given that x and y are both sets, then we're going to use this particular definition. So if x equals y and y equals x, then return true. Okay, so that statement is the same thing as just saying if x equals y returns true, which is the same thing as just return x equals y. Yep. Okay. So now we look at the case. What if x and y are both sets? Okay. Then how do we define equality? This is how we define equality for two sets. X equals y if and only if for all e for every element in x, e is also in y, and for every element in y, e is also in x. So that is kind of something that we saw earlier, which is, if A is a subset of B and B is a subset of A, then A and B are the same set. Okay, it really is kind of saying the same thing, except this time we're using quantifiers. So the more concise way to do this is to say x equals y if and only if for everything in the entire universe, E is an element of x if and only if E is an element of y. In other words, for everything in the entire universe, you might end up with a lot of things that are not in y and not in x. So in those cases, we simply say, well, I guess they are not in either. So if they're not in either, the if and only if is still going to be true. Are we doing okay so far with these notations? And also the application of these notations. Okay, Jonathan says yes. Okay, very good. So we have the example of E equals to x such that P of x. So this notation here really boils down to the same thing here. For everything in the entire universe, x is an element of E if and only if P of x is true. So this notation is kind of a shorthand of this notation here. Alright, so there's a question, there's a comment in the text channel. Basically, for x equals y, their elements must be in each other. Once, so if an element is in x, it has to be in y. If an element is in y, it has to be in x. That's basically what it is. So when we look at the empty set, how do we use a quantifier to describe an empty set? If it is not the case that there exists one thing, at least one thing, such that that one thing is in S, then S is an empty set. So if S is an empty set, this expression would be true. So I'm just basically abusing quantifiers to revisit all the concepts that we have already encountered, because I want to make sure that people understand how to apply the quantifiers and to relate the quantifiers to concepts that we have already understood, being the set operators, what is an empty set, that sort of stuff. We are redefining concepts in Boolean algebra sets / quantifiers. We are relating. It's more like relating, not exactly redefining. We're kind of relating. Intersection and unions. All right, so look at this. So basically, one is for intersection and one is for union. For all x of the entire universe, okay, x is an element of the intersection of a and b if and only if x is in a and x is in b. Now remember, this is if and only if. So if you find something that is in x and in b, that thing, that x, has to be an element of the intersection. On the other hand, if you are given the intersection of a and b, then all the elements in the intersection of a and b, it has to be found in both a and b. Okay, so remember, this is a if and only if. So if you know one side is true, the other side has to be true. Doesn't matter which one we are talking about. If you know the right hand side is true, then the left hand side has to be true. But it also applies when it is false. So if you can say, I can see that a particular element is not in the intersection of a and b. What does that mean? That means this thing here has to be false too. If this is false, this has to be false. In order for this to be false, that means that thing cannot be found in both a and b. Now that still leaves you with three possibilities. It may not be in a or b. It may be in a but not in b. It may be in b but not in a. So you have three possibilities to make that false. But nonetheless, it has to be one of those three scenarios because it cannot A and in B. So you can also see how union is defined very similarly, except the conjunction now becomes a disjunction. So there's a particular reason why the intersection symbol has a resemblance to the conjunction symbol and why the union operator has a similarity to the disjunction operator. So I hope these things kind of help you remember, how the operators relate to each other. Oh, I forgot that we have been skipping Cartesian product. So I will leave it to next or the following class, to talk about Cartesian product. The last one is about subset. A is a subset of B if and only if if you find something in A, that something is also in B. That is subset of. And then proper subset of is the same thing as subset of, but you also have a conjunction here. And then after the conjunction, we say there exists X in B such that it is not the case that X is in A. So in other words, we have something in B that is not in A. So we basically use quantifiers to re-explain the same concepts, the same operators that we have already talked about in basic set theory. So hopefully this will give you guys, a chance to really see how quantifiers are used. Because assuming that you already know the set operators, by redefining those operators in using quantifiers, it will basically help you go like, oh, okay, so we apply the existential quantifier this way, or we apply the universal quantifier in this particular way. Okay, but I do have one thing that I really kind of need to add to the notes, but it's not there yet. So I'm just going to add here. Um, Also, for basic set theory, I don't think we covered infinite sets of even numbers along with Cartesian products. Yes, so we did go over the use of a predicate to qualify what goes into a particular set. We did go over that. So that means, when, in other words, this notation was discussed, in the discussion of basic set theory, even though I did not specifically go through the even number example. Okay, so one more thing, darn it, we are out of time. All right, so I think I'm gonna extend the notes just a little bit, but I think this gives you guys an idea of how to how to take notes, okay? Because at the end of the day, we really want to summarize, revisit all the symbols that we have encountered, find out how they're defined, what do they do, what do they mean, how do they relate to existing concepts that we have already talked about, and so on. That is how we quote unquote understand the concepts, by connecting those by definitions, by derivations in mathematics to things that we already have encountered and understood. So in this class, understanding something is relatively easy to define because we can establish that by using definitions and mathematical derivation. It's a little bit harder to explain what quote unquote understanding means when you're talking about some humanity subjects, because in that case it's a lot more subjective. This class is basically all math. It's really kind of black and white. So I hope you guys have a chance to kind of review what we have talked about today. Kind of refine your notes. Okay, if you are using a mind map, you can expand that. If you're taking notes in any other way, just kind of make sure that you jot down the connections between the symbols, the definitions, and just the logic of everything. All right, so I'm done for today. I am going to write a little bit more in the notes, in the quantifier module. It will be published by the time we meet again on Wednesday. So other than reading ahead of me and reviewing the material, there's no homework assignment. And before someone asks what we are going to talk about next, we'll just go ahead and follow the links. So we are done with basic set theory. We are now done with basic quantifiers. We are pretty much done with set theory using quantifiers except for the Cartesian product. So the next topic that we will talk about, which also means I would like you to have a chance to pre-read before Wednesday, is functions as sets. Okay, and if you are done with that one and go like, oh, that's easy peasy, I'm done, well, go ahead and understand what is injection, surjection, and bijection. So those are the things that we'll be talking about next. All right, so let me see if there are any additional questions. If not, oh, okay, what? I'll see you guys on Wednesday.